Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
What if the biggest mysteries of the universe, how galaxies form, where we even came from, what if they're being unraveled right now in ways we're only just sort of starting to grasp? That's really the question we're diving into today on the Deep Dive. Our mission, as always, is to cut through all the noise, sift through the latest cosmic stuff, and deliver the most impactful insights straight to you. We want you to be informed, but not, overwhelmed. So if you've ever looked up at the night sky and wondered about the incredible forces out there, or maybe even pondered the very beginning of everything, well, then this deep dive is definitely for you. We're heading out on a journey today looking at three pretty astounding stories that stretch from our own sun, like right next door, all the way out to the edges of the early universe. And they're all connected by, groundbreaking observations and some physics that's frankly kind of mind-bending. First up, we'll start by peering into this cosmic dance. Two incredibly massive stars, really big, so close they're literally tearing bits off each other.
And that's revealing some profound secrets about how the biggest stars live, how they die, and ultimately how they seed the universe with the elements that, make us.
Yeah, the building blocks of life, essentially.
Exactly. Then we'll zoom back in, closer to home. We'll get up close and personal with our own sun. We'll see how new satellite data is finally showing us exactly how it flings these super-fast electrons across the solar system. And why that matters for us here on Earth. Even for thinking about trips to Mars, that sort of thing.
And absolutely crucial for space weather.
Right. And finally, we'll take a really audacious leap. We're diving into a radical new idea. One that suggests the very structure of the universe itself. Galaxies. Everything might have formed differently than we thought. Not necessarily by that invisible, super rapid expansion called inflation, but maybe by something we've only recently managed to detect. Gravitational waves. But here's the surprising bit. Maybe inflation isn't needed at all.
And what's truly fascinating here, I think, and it's really the common thread tying all these together, is how cutting-edge technology and just brilliant minds are letting us peel back these layers of cosmic mystery. We're constantly challenging our assumptions about how the universe works. The sheer power of observation driven by these new technologies is letting us see and now even sort of hear the universe in ways that were just completely impossible before.
It's new to the universe, yeah.
From the tiniest, fastest particles shooting off our sun to the grandest structures of the cosmos and the fundamental forces that shaped it all. It's really a testament to human ingenuity, isn't it? And that relentless curiosity we have.
It really is.
Okay.
Let's unpack this first incredible story then. This curve of stars, known as NGC 3603A1. Now, these aren't just any stars. You need to picture two absolutely colossal stars, unimaginably huge. And they're locked in this dizzying orbital tango. It happens almost 100 times faster than Earth orbits our sun.
It's incredibly fast.
We're talking about real celestial giants here. Truly immense. One star is roughly 93 times the mass of our sun.
93.
Yeah, and our sun already dwarfs anything we can easily wrap our heads around. And its partner isn't exactly small either. It's weighing in at about 70 solar masses.
Still enormous.
That huge combined weight makes them one of the heaviest star pairs ever spotted in our entire galaxy. But it's not just their sheer size that's mind-boggling. It's the speed. Well, our Earth takes a whole year to circle the sun. These two, they race around each other in just 3.8 days.
Just under 4 days? Incredible.
Think about that. They complete almost 100 orbits in the time it takes us to do one. And because they're so incredibly close and so massive, the relationship between them is just, incredibly intense. A real cosmic pas de deux. And it's actively changing both stars. Even though they're relatively young, they're influencing each other in really profound, dramatic ways.
And the discovery itself, how we found out about this intense interaction, it's actually a fascinating detective story. It really shows how observation can sometimes be about, revisiting old evidence, but with completely fresh eyes.
Not just a sudden eureka moment, though.
Not at all. It wasn't some flash-in-the-pan thing. It was a painstaking process unfolded over time. Really highlights the human element in science. The crucial breakthrough actually happened in 2020. right in the middle of the pandemic, interestingly enough. An undergraduate student, Sarah Bodansky, was working remotely from Lowell Observatory.
Wow.
And she was meticulously going through older data from the Hubble Space Telescope, data that had probably been looked at by countless astronomers, maybe many times over, spanning years.
Yeah, just sitting there.
Yeah. Exactly. But Sarah spotted something unique, something that everyone else had missed. She noticed that certain spectral patterns, these are like the unique light fingerprints that elements in a star give off. They tell us about its composition, temperature, and crucially, its movement. She noticed these patterns doubled whenever the stars were moving most strongly towards or away from Earth in their orbit.
Doubled. So like seeing two sets of fingerprints instead of one.
Precisely. Imagine a single light source, you see one fingerprint. But if you see two distinct, slightly shifted fingerprints, well, that's a dead giveaway. It means there are two separate sources of light, two stars moving independently, not just one blurred point, which is what everyone thought they were seeing before.
Oh, okay.
This specific doubling of the spectral lines was the key clue. It peeled back the veil, revealed two distinct stars where everyone else just saw one. Honestly, without her sharp insight, her persistence in digging into those subtle details, the project probably would have stalled. This remarkable binary system might have just stayed hidden in plain sight.
That's incredible. Just paying attention to the details.
Absolutely. Her work, really a testament to fresh eyes and careful analysis, eventually led to the publication of these findings in the Astrophysical Journal. And it's worth remembering the incredibly tough environment these stars live in. The system is in NGC 3603. This isn't just a busy neighborhood. It's one of the most densely packed star-forming regions in our whole galaxy.
So crowded.
Extremely crowded, teeming with thousands of other young, bright stars. Only Hubble's incredibly sharp vision, its ability to resolve fine details from huge distances, could even hope to distinguish these two individual stars from that luminous, crowded background, which makes Sarah's initial detection even more impressive, really.
That is an amazing story of persistence, and it really shows how just one sharp observation can completely redefine what we think we know. So if these stars are still, relatively young, what do these incredibly intense conditions actually do to them? Are we seeing them evolve in a unique way? Or is it partly like a visual trick?
That's a fantastic question because what's happening is quite remarkable, and it's actually, well, it's a bit of both. Despite being young, these stars shine so incredibly fiercely, and they blast out such strong stellar winds, these streams of charged particles constantly flowing out that they actually look like much older, dying stars, stars we call Wolf-Rayet stars.
Wolf-Rayet stars, those are the really old, massive ones nearing the end, right?
Exactly. Typically, Wolf-Rayet stars are massive stars in their final stages. They've shed most of their outer hydrogen layers, revealing their hotter, denser helium cores. They're usually on the brink of collapsing into a black hole or exploding as a supernova.
Okay.
But these NGC 3603A1 stars, they're still youthful, pretty much in their prime. It shows that extreme conditions, like this rapid orbit and their immense gravity pulling on each other, it can actually accelerate their apparent aging. It makes young stars look much older than they really are.
Well,
It's like seeing, I don't know, a teenager with the deep lines and weathered look of an old sailor, just because of the incredibly intense environment they're living in.
so it's not just a visual trick. It's like a physical mimicry driven by their surroundings. And this intense interaction, it isn't just cosmetic, right? You said it's actively shaping their evolution. What kind of changes are we actually talking about? Are they literally, like we said at the start, tearing each other apart?
Oh, absolutely. It's a very dynamic and, yeah, quite a destructive relationship. The evidence strongly suggests that the smaller of the two stars has actually stolen material significant amounts of mass from its larger companion.
Stolen material. How does that even work between stars?
It happens through a process we often call Roche-Lobe overflow. It sounds complicated, but basically imagine each star has a gravitational zone of influence around it. It's Roche-Lobe. When they get this close, and one star naturally expands a bit as it evolves or maybe just puffs up, it can overflow that gravitational boundary. And then its material gets pulled away by the stronger gravity of its companion star.
Like a stream flowing from one to the other.
Exactly, a continuous stream of stolen material. And this has had a profound effect on the star receiving the material. It's caused the smaller star to spin much, much faster, like an ice skater pulling her arms in to speed up her rotation.
Ah, conservation of angular momentum.
Precisely. And this whole process is absolutely vital for scientists because it helps them understand the really complex ways massive stars change over their lives, how they create and distribute heavy elements, the stuff we're made of, and what their ultimate often spectacular ends might be. Usually astronomers have to rely on these complex, often quite uncertain models to estimate the mass of stars, especially single ones.
Right, it's a best guess situation.
Pretty much. But in special systems like NGC 3603-A, where you have two stars orbiting so closely and so rapidly, scientists can actually measure their masses much more directly just by carefully observing their orbital mechanics, how they move around each other. This gives us invaluable, precise data. It refined their understanding of stellar evolution. It's like having a precise cosmic scale instead of just a good guess.
Like finding a cosmic Rosetta Stone for understanding these giant stars. That's fantastic. Okay, so that's an incredible insight into how these stellar behemoths live. But thinking about their end game, the ultimate fate of stars this massive, what happens when they finally do collapse?
Yeah.
And crucially, how does that connect to those mysterious ripples in space-time we've been hearing so much about lately? Gravitational waves.
Right, and that's exactly where these systems become true cosmic game changers, particularly when we start thinking about gravitational waves. Stars, this incredibly massive, when they finally run out of fuel and reach the end of their lives, they are destined to collapse under their own immense gravity. And what they form are black holes.
Black holes, right.
Now, if both stars in such a close binary system eventually become black holes, and given their huge masses, that's a very strong possibility, maybe even likely, they would continue to orbit each other, maybe for billions of years, forming what we call a binary black hole system.
Two black holes orbiting each other.
Exactly. And over vast cosmic timescales, these two black holes would relentlessly spiral inward, losing energy through gravitational radiation, drawing closer and closer, until they eventually merge into an even larger, single, more massive black hole. And this monumental merger event, this collision of two singularities, would send out incredibly powerful ripples in the very fabric of space-time itself. Those are the gravitational waves we're talking about.
The ones LIGO detected.
Precisely. Since 2015, as you mentioned, scientists have had this incredible capability to detect these waves using ground-based observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO effectively listens for the faint echoes, the chirps of these cataclysmic events happening across the universe. So research into systems like NGC 3D603A1 is absolutely crucial. It helps us better predict where and maybe even when these cosmic collisions of black holes might happen out there.
So finding the nurseries for future gravitational wave events.
You got it. It's like finding the places where these events are born. It opens up a whole new window for observation, letting us hear the universe in a way we never could before. And, it really raises an important question. What other powerful cosmic events, maybe beyond merging black holes and neutron stars, might be sending us these subtle, profound ripples across the universe? Ripples just waiting for us to listen. Could there be echoes from the very beginning of time itself?
That's an amazing thought. Echoes from the dawn of time. It's incredible to think about these distant titanic dances shaping the universe and sending out these gravitational whispers. But sometimes the most dramatic and impactful forces are actually much closer than we think. Let's bring our focus back home now to our own cosmic neighborhood and specifically to our sun, which it turns out is also a surprisingly dynamic and volatile engine. It's constantly throwing out streams of highly energetic particles, maybe not on the scale of those giants, but still significant.
Very significant for us.
We know it's constantly chucking out these incredibly energetic particles, including electrons that can reach almost the speed of light. But until really recently, the how and the why of these super fast electrons, it was still a bit of a mystery, wasn't it?
It really was.
And understanding them is absolutely vital, right?
It truly is. These particles, we call them solar energetic electrons, they're crucial for understanding what we call space weather. And space weather directly impacts our technology, our critical infrastructure here on Earth, and definitely our expanding presence out in space. For a long time, scientists knew these electrons came from solar activity, mainly things like solar flares and these big eruptions called coronal mass ejections, or CMEs.
Flares and CMEs, okay.
But the detailed mechanisms, how they get released from the sun in the first place, how they get accelerated to such incredible speeds, and then how they travel through the vastness of space, that was all still pretty unclear. It was a significant gap in our understanding. Almost like, I don't know, knowing a cannon fired something, but not understanding the gunpowder, the fuse, or the trajectory it took.
Right, missing the crucial details. And that's precisely the challenge the Solar Orbiter spacecraft set out to tackle. We needed to get closer, didn't we? What was its big advantage in cracking this mystery?
Absolutely. Getting closer was the key. The sheer difficulty of tracking these tiny, super fast particles from way back here near Earth, It meant their origin signatures, the clues about where and how they started, were often blurred or just lost by the time they reached our satellites.
Like trying to trace a ripple in a pond from miles away.
Exactly that. The Solar Orbiter, which is a joint mission between the European Space Agency, ESA, and NASA, it had a huge advantage. Its orbit is highly elliptical, and it swings much closer to the sun than any previous mission managed consistently. Sometimes it gets as close as Mercury's orbit.
Wow, that's close.
Very close. And between 2020 and 2022, it was able to observe over 300 distinct electron events, much nearer to their source than we ever could before. This proximity was absolutely critical. It let them measure the electrons, their energies, their initial directions before their paths got too messed up, too diffused, by traveling long distances through the turbulent environment of space.
So catching them fresh, basically.
Pretty much. And the core discovery from all this data is really groundbreaking. It turns out there are actually two distinct ways the sun produces these fast electrons, and Solar Orbiter could finally tell them apart.
Two different mechanisms.
Yeah. First, some electrons are directly linked to solar flares. These are those sudden, incredibly intense explosions from relatively smaller, localized regions on the sun's surface. Think of them like a very focused, powerful blast furnace kicking off.
Okay. Quick and intense.
Exactly. These flares produce sharp, almost instantaneous bursts of electrons that rush out quickly, like short, intense blasts from a high-pressure hose. Then there's a second, quite different mechanism. This one is tied to much larger, more expansive eruptions, the coronal mass ejections, the CMEs.
The big ones.
The really big ones. These are when...
Okay, so it's not just that the sun emits these particles, but how it does it. And there are different styles, if you like. But here's that surprising twist again. For years, scientists noticed something odd. It sometimes looked like there was a long, kind of puzzling delay between when you'd see an outburst on the sun, a flare or a CME, and when the energetic electrons actually showed up at spacecraft near Earth. This delay was a real head-scratcher, wasn't it? Why the lag? Was the sun just slow off the mark sometimes? Or was something else going on?
Exactly. That was a persistent mystery. You'd see the flash on the sun, you'd expect the particles pretty quickly given their speed, and then there'd be this frustrating, unpredictable gap. The Solar Orbiter's close-up views finally gave us the answer. And it turns out it has everything to do with the journey, not the departure time.
The journey.
Yeah, the environment these electrons have to travel through. You see, electrons don't just fly in a straight line, totally unimpeded out from the sun. The space between the sun and the planets, the heliosphere, it isn't empty. It's filled with the solar wind.
Right, that constant stream of particles.
Exactly. A constant turbulent flow of charged particles and critically tangled shifting magnetic fields coming from the sun itself. This solar wind isn't some calm river. It's more like a chaotic, constantly shifting ocean current.
Okay, turbulent.
Very turbulent. So as these super-fast electrons race through this chaotic environment, they don't just sail through smoothly. They get scattered, they get bounced around, delayed, redirected by these complicated magnetic field lines, and by bumping into other particles.
Like trying to run through a really dense, moving crowd.
That's a great analogy. You might eventually get to where you're going, but your path will be anything but straight, full of detours, delays. It'll definitely take longer than if you had a clear run.
Got it. So the delay isn't usually a problem at the sun's end. It's more like a tough commute for the electrons.
Precisely. This scattering and redirection makes them appear to arrive later than their actual launch time from the flare or the CME. So, by comparing hundreds of these electron events, seen at different distances from the sun thanks to its orbit, the Solar Orbiter researchers could meticulously sort out these travel effects. It's like they could untangle this complex knot. They could differentiate any real delays in the sun's emission, if there were any, from the delays caused purely by the electron's difficult journey through the solar wind.
Okay.
And that allowed them to pinpoint exactly when and where the electrons were really launched from the sun. It cleared up a long-standing mystery and gives us a much, much clearer picture of the sun's particle-flinging dynamics. It really revolutionizes how we understand these energetic particles getting to us.
Okay, so with this much clearer picture, what does this actually mean for you, for us, back here on Earth, or thinking about going into space? How does this deep dive into solar electron physics translate into, real-world impact?
Well, the impact is potentially huge. These energetic electrons, especially the ones churned out during those large CMEs, they can be quite dangerous. Knowing their origin and their likely path much more accurately is a game changer for space weather prediction.
How are they dangerous?
They pose significant risks to our critical infrastructure. Satellites, the ones powering our GPS, our communications, weather forecasting, they can experience malfunctions, disruptions, sometimes even permanent damage when these high-energy electrons slam into sensitive electronics. For astronauts on long missions, say to the Moon or Mars, outside the protection of Earth's magnetic field,
Yeah.
these electrons increase their radiation exposure. That can lead to health issues, anything from short-term radiation sickness to a higher long-term risk of cancer and DNA damage. And they can even affect things on the ground. They can induce powerful electrical currents in power grids during strong geomagnetic storms, potentially causing widespread blackouts. We saw that happen in Quebec back in 1989.
Right, I remember that.
So being able to distinguish which type of solar event, was it a quick flare or a big, slow CME, is producing these particles. It gives scientists a much better shot at predicting not just when strong space weather might hit, but, crucially, how severe it's likely to be.
Better forecasting, basically.
Much better. This knowledge directly improves our ability to protect satellites, to safeguard astronauts, and even to mitigate potential impacts on our power grids here on Earth. The solar orbiter's work really confirms, beyond doubt, that our sun isn't just our friendly neighborhood star giving light and heat. It's also the most powerful particle accelerator nearby. And it shows us, in amazing detail, how its eruptions shape the space weather that can seriously affect Earth and our technology.
That's incredible, going from a kind of theoretical mystery about delays to actually having practical tools for protecting our future both in space and here at home. And this isn't just a one-off success story, right? Part of a bigger ongoing effort to understand the sun. What's next?
Oh, absolutely. It's a continuous story of discovery, definitely not the end. The Solar Orbiter mission itself has already created this incredibly detailed catalog of electron events. And they've made this data available to researchers all over the world, which is fantastic for fostering more science. Looking ahead, the European Space Agency, ESA, has even more ambitious plans to boost our prediction skills. For instance, there's ESA's Vigil mission, which is planned for launch around 2031.
Vigil.
Yeah, Vigil. It's going to take things to the next level. Instead of watching the sun from near Earth, Vigil will position itself way off to the side. It will watch the part of the sun that's rotating towards Earth, but which Earth can't actually see yet.
Like an early warning system.
Exactly. It could give us crucial early warnings of potentially hazardous eruptions days, maybe even a week, before they rotate into view and potentially head our way. That gives us valuable lead time to prepare.
That's huge.
It is. And there's another upcoming mission called SMILE that's a joint ESA-Chinese mission. SMILE will focus specifically on how Earth's own magnetic field, our magnetosphere, reacts when these solar storms hit it, giving us deeper insights into our planet's natural shield and the complex physics of how space weather interacts with us.
That's truly an incredible leap forward in our ability to predict and prepare for these cosmic events, all thanks to focused observation and some really clever spacecraft design. It really shows how far we've come in understanding our nearest star and its impact on us. Okay, but let's take an even deeper dive now. Let's step back from the sun and look at maybe the biggest question of all. How the universe itself began and how it got its structure. You know, galaxies, stars, planets, eventually even us. For decades, the leading theory to explain all that has been something called cosmic inflation. This idea of an unimaginably rapid expansion right after the Big Bang, which supposedly smoothed everything out and planted the seeds for galaxies.
Indeed. For many years now, the prevailing view among most cosmologists has been exactly that. The Big Bang marks the start, but it was immediately followed by this incredibly brief but extraordinarily rapid phase of expansion called inflation. We're talking tiny fractions of a second here, like 10 to the minus 36 up to 10 to the minus 32 seconds after the Big Bang. In that instant, the theory goes, the cosmos expanded exponentially. It grew from way smaller than an atom to, well, macroscopic sizes almost instantaneously.
Mind-boggling speed.
Absolutely. And this rapid expansion, its proponents argue, did a couple of crucial things. It smoothed out any initial wrinkles or irregularities, which helps explain why the universe looks so remarkably uniform, so similar on very large scales today. This helps solve what cosmologists call the horizon problem, why distant bits of the universe look the same even though they shouldn't have had time to influence each other back then.
Okay, so it explains the smoothness.
Right. And inflation also provides a compelling mechanism for where structure came from. Tiny quantum fluctuations present in the very early universe would have been stretched out to cosmic scales during this exponential expansion. And these stretched out fluctuations then acted like the seeds. Over billions of years, gravity pulled matter towards these slightly denser regions, and they grew into the vast structures we see: galaxies, clusters of galaxies.
Seeds of everything.
Pretty much. It also offers a neat solution to the flatness problem, explaining why the universe's overall geometry seems incredibly flat, not curved. However, and this is a big however, while inflation has been incredibly powerful and successful in explaining these big cosmological puzzles, it does rely on several variables and some hypothetical elements that have never actually been directly observed or verified. Well, for instance, it requires the existence of a hypothetical energy field, often called the inflamed field. This is the field that supposedly drove the rapid expansion. But its precise properties, what it actually is, are still unknown. It's something we've had to postulate. This reliance on, let's say, unverified ingredients has naturally left the door open for alternative ideas and, frankly, ongoing debate among cosmologists. And it raises a really important question. Can we explain the universe's beginning, its structure, with simply physics? Physics we already know and have verified without needing to invent new stuff.
That is a really important distinction. Because, yeah, while inflation solves some big problems, it does introduce these new, unproven elements. So what if that super fast inflation just wasn't necessary at all? And here's where we get that truly mind-bending insight we teased earlier. A new study published in Physical Review Research by a team from Spain and Italy brings a completely fresh perspective to this ancient mystery. They're basically suggesting that maybe, just maybe, this rapid inflation phase isn't required to explain how the universe formed and got its large-scale structure.
And this is where the implications get really profound. Their core idea revolves around gravitational waves. Those ripples in space-time we talked about earlier, caused by massive accelerating objects, the ones LIGO proved exist.
Right.
They suggest those might actually hold the key to understanding how the cosmos emerged from the Big Bang and how it structured itself. And what's particularly compelling about their model, I think, is its elegance and simplicity. Instead of having to introduce speculative new fields or exotic particles we've never seen, their proposal builds entirely on well-established physics.
Physics we already know works.
Exactly. The existing frameworks of gravity, Einstein's general relativity, and quantum mechanics, the pillars of modern physics. They connect this idea to a mathematical framework called de Sitter space. This is a concept developed way back in the 1920s by Willem de Sitter, a Dutch mathematician who actually worked with Einstein on early cosmological models.
De Sitter space.
Essentially, de Sitter space describes a universe that's expanding exponentially, but, and this is the crucial part, it does so without needing any matter or radiation to drive it. Instead, its expansion is driven purely by a positive cosmological constant, which is basically the energy inherent in empty space itself, the vacuum energy. That's a concept very much part of Einstein's original equations.
So an expanding universe, but driven differently.
Driven by the vacuum itself, yeah. It's a foundational, somewhat idealized model in cosmology, but it provides a simpler stage to explore the very, very early universe, long before stars and galaxies even formed. And the appeal of their approach, according to one of the co-authors, Raul Jimenez, is precisely this elegance. He says, and I'm quoting here, "The new model does not require unverified ingredients. It suggests that the interplay between gravity and quantum mechanics alone might be sufficient to account for the universe's origin and large-scale structure," which basically means they're leaning only on fundamental concepts that scientists have been working with and verifying for over a century, rather than needing to invent new components just to fill the gaps left by the Big Bang.
That is a truly powerful statement, relying only on known physics. But, for decades, inflation has been the dominant idea. What are the potential weaknesses or maybe the unresolved issues that a model like this, based on gravitational waves, might face, especially when it's challenging such an established theory?
That's a very fair question, and it really gets to the heart of the ongoing, healthy debate in cosmology. Science thrives on these challenges. The primary hurdle for any alternative to inflation, including this gravitational wave model, is whether it can explain all the precise observations that inflation currently accounts for. Particularly the incredibly detailed map we have of the cosmic microwave background radiation, the CMB, that's the afterglow of the Big Bang. Inflation makes very specific predictions about its uniformity and the pattern of tiny temperature fluctuations within it, the ones that grew into galaxies.
Right, the detailed pattern in the CMB.
Exactly. While this new model is elegant, The detailed calculations of exactly what kind of CMB pattern it would produce might differ subtly from inflation's predictions. The key will be future, even more precise observations of the CMB. And also, critically, a dedicated search for primordial gravitational waves, ripples, not from black holes merging, but from the Big Bang itself.
Gravitational waves from the beginning.
Yes. Detecting those and measuring their properties would be a crucial test. Inflation predicts a certain type or spectrum of these primordial waves. If we detect something different, or maybe nothing at all within certain limits, that would really shake things up. So it's a really active area of research right now, both theoretically and observationally, trying to find ways to distinguish between these different origin stories.
And it's fascinating that we're even talking about gravitational waves as a potential architect of the universe, given their history. It's a concept that went from pure theory to actual detection relatively recently, right? Could you walk us through that journey?
Absolutely. It's a fantastic story in the history of science. The idea of gravitational waves wasn't some sudden revelation. There were early hints in the work of people like Oliver Heaviside back in 1893 and Henri Poincaré in 1905. They were grappling with gravity and electromagnetism. But it was really Albert Einstein in 1916 who fully developed the concept as a direct consequence of his general theory of relativity.
General relativity, the curved space-time idea.
Exactly. In that revolutionary theory, Einstein showed that space and time aren't just a static stage, but a flexible, dynamic fabric. And this fabric gets warped and curved by mass and energy. The classic analogy is a bowling ball on a stretched rubber sheet. So Einstein realized if massive objects accelerate like two black holes spiraling into each other, or the core of a giant star collapsing in a supernova, or two super-dense neutron stars colliding, they should create disturbances, ripples in this space-time fabric, like dropping a stone into that metaphorical pond. And these ripples would then spread out across the cosmos at the speed of light. Those are gravitational waves.
But they were hard to find.
Extraordinarily difficult. Einstein himself initially doubted we could ever detect them. Their effects are incredibly tiny. They stretch and squeeze space-time by amounts far smaller than the width of an atom, even when passing through something as large as the Earth, after traveling for billions of years.
Wow, minuscule.
For decades, they remained purely a theoretical prediction. A testament to Einstein's genius, sure, but unproven experimentally. It was only in September 2015, almost essentially after Einstein's prediction, that the incredibly sensitive instruments of LIGO, the Laser Interferometer Gravitational Wave Observatory, finally succeeded.
LIGO, those giant L-shaped detectors.
That's right. Essentially two giant detectors, one in Louisiana, one in Washington state, with arms several kilometers long. They use lasers to measure tiny changes in the length of those arms. And in 2015, they detected this faint chirp signal, the signature of two black holes merging over 1 billion light years away.
A monumental discovery.
Absolutely monumental. It confirmed Einstein's prediction and opened up an entirely new era in astronomy. It gave us a new way to see or hear the universe, not just with light, but with gravity itself. A revolutionary new sense for cosmic exploration.
So, bringing back to this new idea, what does it all mean if gravitational waves, these ripples, were actually the architects of the early universe, instead of some hypothetical inflation field? That feels like a really dramatic shift in how we think about the beginning.
It absolutely is a dramatic shift, potentially. It challenges the very notion that inflation is the sort of unavoidable, preordained starting point for the universe's structure. It suggests a potentially simpler, maybe more elegant explanation. One relying only on known physics, that fundamental interplay between gravity and quantum mechanics might actually be enough to explain how order emerged from the primordial chaos of the Big Bang, without needing to add extra, unproven assumptions or ingredients like the inflaton field.
So the universe sculpted itself using the physics we already knew.
That's the intriguing possibility they're exploring. Imagine the very fabric of reality itself, right at the beginning, wasn't just a blank canvas waiting for some inflatoon to paint on it, but maybe it was already a vibrating, humming space-time, singing the song through gravitational waves that sculpted the first structures, the seeds of galaxies. It really challenges us to rethink the universe not just as a stage, but as a dynamic, constantly resonating medium right from the word go.
That is a profound thought, a resonating universe. And it's important, like you said, to reiterate that the Big Bang model itself still stands. That's still our best framework for the universe's origin and evolution. This new research doesn't overturn the Big Bang, does it? It's more about questioning what happened right at the very, very beginning, or maybe what mechanisms guided those earliest moments.
Exactly. The Big Bang theory describes the universe expanding from an incredibly hot, dense state. That core idea is incredibly well supported by evidence like the CMB and the abundance of light elements. But the questions about what happened right at time zero, or even what happened just before the expansion we can observe, or what were the precise mechanisms that guided those first tiny fractions of a second, those remain largely unanswered. They're right at the edge of our current understanding. So each new approach, like this one focusing on gravitational waves, provides another potential piece of the puzzle. It pushes the boundaries of what we can imagine, and crucially, what we might be able to test with future observations. It keeps the whole field dynamic and constantly evolving. It ensures the universe always holds new surprises for us.
Absolutely. Okay, as we wrap up this deep dive, let's just quickly recap the incredible journey we've been on. It's been quite a ride. We started way out there with the violent birth of potential black hole progenitors, those two incredibly massive binary stars, NGC 3603-A1, locked in that furious dance,
Sure.
learning about stellar evolution and the very origins of the gravitational waves that are now giving us this new cosmic sense.
Mm-hmm.
Then we zoomed right back in to our own sun, peering into its workings with the solar orbiter, precisely mapping those dangerous electron outbursts that drive space weather, and seeing how that drastically improves our ability to predict and prepare, protecting our technology and future astronauts.
It's a very practical outcome.
Definitely. And finally, we explored this potentially revolutionary new way of thinking about the very fabric of the early universe, where gravitational waves, maybe not cosmic inflation, might have been the sculptors, relying only on that elegant dance between gravity and quantum mechanics. And throughout all this, we've seen that crucial human element, haven't we? From the sharp insight of a curious undergraduate, Sarah Bodansky,
Incredible story.
to the amazing precision engineering of a spacecraft like Solar Orbiter, and the bold, innovative thinking of cosmologists just pushing the boundaries of what we know about existence itself.
And if we try to connect all these threads, looking at the bigger picture, all these deep dives, whether they're into massive stars or the dawn of time itself, they're all powered by our growing ability to observe the universe in profoundly new ways. We're not just using visible light anymore, are we? We're observing through particles, through radio waves, gamma rays, and now, incredibly, through these ripples in space-time itself.
Our cosmic toolkit is expanding.
Massively. And this constant evolution in our observational power is what lets us challenge those long-standing assumptions, find unexpected answers that were maybe hidden in plain sight all along, and continually refine our understanding of the fundamental forces that govern everything, from the smallest electron zipping away from the sun to the largest galaxy cluster. And hopefully, you listening have just gained a shortcut to understanding some of this really cutting-edge science without getting totally bogged down in the technical jargon. That's really what we aim for here. It just reinforces the idea that knowledge is never static, is it? It's a living, breathing thing, constantly evolving with every new observation, every new theory.
Beautifully put. You know, Carl Sagan once reminded us so eloquently that we are made of star stuff, emphasizing that the cosmos isn't just out there, it lives within us, and that through science, we are, in a way, the universe becoming aware of itself.
A wonderful thought.
It really is. And this deep dive today, whether we were observing distant, furiously orbiting stars, or mapping the sun's powerful eruptions right next door, or even contemplating the ripples of creation that might have shaped the universe's dawn. It isn't just about understanding the universe's origins in an abstract way. It's maybe about understanding our own place within it, our deep connection to this grand cosmic narrative, a story that's still being written, still revealing its secrets every day. So the final thought to leave you with is, what other fundamental assumptions, what other things we take as given about the universe might be waiting just around the corner, waiting to be challenged by the next observation, the next bold insight? Keep exploring, keep questioning, and please do join us next time for another deep dive into the knowledge that shapes our world.